Hello everyone. Today we're going to be learning about section 10.6 and alternating series. So in section 10.5 we did comparison tests. And comparison tests are really good for trying to figure out if certain series converge. One of the downfalls with comparison tests, however, is that they don't work for series that have negative terms. And the alternating series helps us to capture some of that lag. So in this section, we're going to be learning how to deal with certain series that have alternating terms. In particular, let's consider the alternating harmonic series to start. So remember that an alternating series is a series that alternates in sign. And so it has positive and negative terms. In section 10.4, we learned that the harmonic series, the sum from k equals 1 to infinity of 1 over k, diverged, because that's a p-series where p is equal to 1, which is less than or equal to 1. So now let's consider the alternating harmonic series. As you might have guessed, it is the same exact thing, except now we have negative 1 to the k plus 1 in the numerator. We also can use negative 1 to the k. It's really essentially the same thing, but for now we'll just consider negative 1 to the k plus 1. So that is the same thing as the harmonic series, except the terms alternate in sign. We have positive, then negative, then positive, then negative, then positive, etc. Okay, so now let's consider the partial sums for these values. So S1, the sum of the first 1 terms of this series, is just 1. It's just the first term. S2 is the sum of the first 2 terms, so 1 minus 1/2, of course, is just 1/2. S3 is the sum of the first 3 terms, so we can take S2 plus the third term of the series, which in this case is 1/3. So 1/2 plus 1/3 is just 5/6. S4 is S3 plus the fourth term of the series. In this case, that is negative 1/4. And we get 7/12 when we add that together. S5 is just S4 plus the fifth term of the series, which is 1/5. And when you take 7/12 plus 1/5, you're going to get 47 over 60. All right, so it may not be totally obvious at this point, but what you will notice is if you start to take this sequence of partial sums out even further, is that they actually seem to approach a single number. In other words, the limit of this sequence of partial sums converges. And that indicates that the entire series would converge. Remember, if you take the partial sums and the limit of the partial sums equals some number, then the limit of this, then the series converges to that number. So some graphical evidence is over here on the right. We start off with the partial sum S1 being right here. Here's S2. This is S3. And then S4, S5, etc. And you'll notice they get closer and closer to this number here, which is like just less than 0.7, so maybe like 0.695 or something. Don't know exactly what that is, but just kind of a guess. And that indicates that this series should converge, which is kind of remarkable because our original series up here, the regular harmonic series, diverged. And so our claim is that the alternating harmonic series converges. And in fact, there's a simple test associated with with alternating series that we can use to determine whether or not it converges or diverges. And that is called the alternating series test. So the thing that is great about alternating series is that we only need to check 2 things to know whether or not this converges or diverges. So the 2 things that we need to check for our series is that the terms of the series are non-increasing in magnitude. So in other words, if we start off with the series of negative 1 to the k plus 1 times ak, so ak is defined to be everything except that negative 1 to the k term. If the AK term is non-increasing, in other words, it's decreasing, then, so that's the first condition. We need that AK is non-increasing or decreasing, and the limit of AK is equal to 0, then the series will converge. So it only needs to satisfy those two conditions, decreasing and limit is 0. Okay, so in other words, if ak is not increasing after some index k equals n, and the limit of ak is equal to 0, then the alternating series converges. So whenever I say k equals capital N here, basically what I'm saying is that it can grow for a little bit. So let's imagine that ak looked like this. You know, it's a sequence, it grows for a little bit, but then after some point, it decreases forever. Right? It looks something like this. So it can grow for a while, but then after some capital N, it has to decrease forever. That's essentially what we're saying there. So we only really care about the long-term behavior of AK. We don't really care about what happens in the short term. It can increase in the short term. All right, so that's essentially what I've written down here. It's okay if it increases up to some point and decreases forever after that point. All right, so now we're going to do some examples. We're going to identify AK and determine if the series converge or diverge. So in this first example, this is the alternating harmonic series. The idea is that AK is everything except for this -1 to the k plus 1 term. So in this case, AK would just be 1 over k, right? And so we need to check two things. We need to check, one is AK non-increasing. And in this case, it is. There are two ways in this section that you can check for whether something is non-increasing. The first way is to take a derivative. So just like we did in the integral test section, we can take a derivative if the derivative d by dx of 1 over x is less than 0, or we can say less than or equal to 0. For all x within 1 to infinity, then AK is decreasing. Decreasing. Okay. In this section, we can also, I think I accidentally erased this over here. We can also do this thing. We can say if AK plus 1 is less than or equal to AK, then it is decreasing. Then AK is, I should technically say non-increasing. I'm going to use these terms pretty interchangeably, even though they do technically mean different things. All right, so in this case, AK plus 1 is less than or equal to AK, and we can show this because we know that K plus 1 is greater than or equal to K, and that implies that 1 over K plus 1 is less than or equal to 1 over K, which is the same thing as saying A sub K plus 1 is less than or equal to AK. And this is true for all K. So technically, we don't need to show that it's true for all K. We only need to show that it's true for all K sum past some capital N. But in this case, it's true for all K that are positive. All right, so that's either one of these methods, method A or method B, are sufficient to show that a sequence is non-increasing. And in this case, 1 over k is non-increasing. Okay. I didn't actually take the derivative, but if you did that, then you would see that as well. All right, so actually I would argue this is the harder step, figuring out whether it's non-increasing or not. The easier step is the calculus, is taking a limit. So in this case, the limit as k approaches infinity of 1 over k, well, that's 0, right? We don't have to show any work. We just know that's true, because 1 over infinity is 0. So yes, that's good. And so therefore, we would write our conclusion, use a different color. So therefore, by the alternating series test, the sum from k equals 1 to infinity of -1 to the k plus 1 over k converges. All right, so this series converges because it satisfies both those criteria. All right, so the next thing to check is this second example, B. So this one's a little bit more difficult because we have to first of all figure out how to write this as a series. So let's think about it. In the numerator, the numbers are always increasing by 1. And in the denominator, the numbers are always increasing by 1 as well. But it's 1 less than the numerator. So we could write this as k plus 1 over k. And let's double check that to make sure it makes sense. If we were to plug in k equals 1, then we would get 1 plus 1 over 1. So we would get 2 over 1. All right, so I have made a slight mistake here. Go back. This alternates, and so we do need a -1 to the k term here. And to figure out if this is -1 to the k or -1 to the k plus 1, we just need to think about what happens to the first term. If we plug in k equals 1 into this series, we would get 2 over 1 times -1 to the 1, which would be -2 over 1. But our first term is actually positive, so that indicates that we should make this a k plus 1 instead. And so now if we plug in k equals 1, we would get 2 over 1, minus 3 over 2, plus 4 over 3. And finally, yeah, we would keep going. And this works out, which is exactly what we want. So this is the series format for what this series looks like. All right, so now we have to identify AK. In this case, AK is everything except that -1 to the k plus 1 term. So it is just k plus 1 over k. So now we should check to see if this series is non-increasing and its limit is 0. I'm actually going to check the second condition first. So we need to check if its limit is not equal to 0. So is the limit as k approaches infinity of k plus 1 over k equal to 0, question mark. And in this case it is not, because we know that this limit is equal to 1. Since it's equal to 1, the idea is that rather than saying that this diverges by the alternating series test, we're actually going to go all the way back to the divergence test that we learned back in section 10.4. And we are going to say that this entire series will diverge. So we can say that the limit as k approaches infinity of k plus 1 over k times -1 to the k plus 1 This series actually oscillates between -1 and +1 as k gets closer and closer to infinity. If you consider just the odd terms and just the even terms, let's write it like this. So, if k is odd, then you would get, as a power for this -1 term, you would get even powers. And so that would indicate that you're multiplying by +1. So this is equal to 1 if k is odd. And if k is even, then the -1 power will have odd powers of k. And so that would indicate that you're multiplying by -1. And so this limit is equal to -1 if k is even. Since these limits are not the same, this limit diverges. Therefore, it diverges by divergence test. So let me write that. So we'll say that this is not equal to 0. So by divergence test, the series of k plus 1 over k times -1 to the k plus 1 diverges. All right, so the main thing to take away here is that the alternating series test doesn't have an official way to say that something diverges. We always refer back to the divergence test. Okay, let's do another example. Suppose we want to consider the sum from k equals 1 to infinity of cosine of pi k times k divided by e to the e to the 0.1 k. All right, so here we don't really have a really obvious -1 to the k term, but what I claim to you is that cosine of pi k is the same thing as -1 to the k power. All right, to see that, think about what happens at k equals 1 or let's consider a bunch of different k for these guys. So here's k. And cosine of pi k. All right, so let me just verify to you that these indeed are the same. If k is equal to 1, 2, 3, 4, if we plug in 1 into -1 to the k, we would get -1. If we plug in 1 into cosine of pi k, then we have cosine of pi, which is -1. If we plug in 2 into -1 to the k, we would get -1 squared, which is just 1. If we plug in 2 into cosine of pi k, we would get cosine of 2 pi. That is 1. If we plug in 3, we would get -1 for both. If we plug in 4, we would get 1 for both. And this continues on and indefinitely. So the claim is that cosine of pi k is indeed equal to -1 to the k. There's a similar thing that you can do with sine, but you have to do like a weird sum inside the sine thing. All right, so in this case, our AK is just going to be everything that's not cosine of pi k, so it's just k over e to the 0.1 k. And we have to check two things. A, is this thing decreasing? And B, is the limit equal to 0? So 1, let's check non-increasing. In order to do this, I'm going to recommend that we take a derivative here. It's a little bit too difficult to determine whether the thing is non-increasing otherwise. So we're going to take a derivative, d by dx. We're going to change everything to x's, so we have x over e to the 0.1x. All right, so when we use the quotient rule, we will get e to the 0.1x minus x times 0.1 e to the 0.1x divided by e to the 0.1x, that whole thing squared. If we factor out a e to the 0.1x on top, we're going to get 1 minus 0.1x, and then still divided by e to the 0.1x squared. Okay. Since there's an e to the 0.1x on top and an e to the 0.1x on bottom, those can actually cancel out, and we are just left with 1 minus 0.1x over e to the 0.1x. Okay, so here's the question. Is this thing less than or equal to 0? Well, if x was equal to 5, then that's not true. This thing would not be less than or equal to 0. But if x is equal to 25, then it would be true. Notice that the denominator is always going to be negative. Or sorry, the denominator, this thing, is always positive. But the numerator is negative only for x greater than or equal to 10. Okay, so let's write that down. This thing is greater, or sorry, I keep messing up. This thing is less than or equal to 0 for x greater than or equal to 10. So if x was larger than 10, then this whole entire thing would be negative. And that indicates that this thing here, this 10, that is my capital N that I was talking about earlier. It increases, this series increases up to some point, but then after that point, after k equals 10, it will always be decreasing. And so yes, it is non-increasing after k equals 10. Okay. The second thing that we should check is whether the limit is 0, and once again, I argue that this is simpler. Of ak. Remember, we don't include that cosine of pi k. We're just taking the limit of ak. So as k approaches infinity, we get k over e to the 0.1 k. All right, there's two different ways you can look at this. You could either do L'Hopital's rule, or you could notice that the growth rate of the top is a polynomial, and the growth rate of the bottom is an exponential. So either way, you're going to get that this thing is equal to 0. So in this case, we're going to say because k grows a hell of a lot slower than e to the 0.1k. All right, so this series satisfied both conditions, namely that it was non-increasing and that the limit was 0. So we are going to write our conclusion in words. We're going to write that, therefore, the sum from k equals 1 to infinity of cosine pi k times k all over e to the 0.1k converges by the alternating series test. And yes, you can abbreviate that on an exam. Okay, great. So, in case it wasn't clear, there's a specific theorem in this book that illustrates that the alternating harmonic series converges, even though the harmonic series diverges. And that was shown in example A 2 slides ago. And we also know that the alternating harmonic series can look like this, where instead of a k plus 1, we just have a k. That also converges. Okay. Now let's talk about remainders for alternating series. So the thing that's nice about alternating series is that there is a very easy way to check the error or the remainder of your alternating series. So first of all, we are going to let S be the infinite series, and we are going to suppose that it is a convergent series. So we know that there is some true value for S. S is finite. All right, so the idea here is that the remainder, the absolute value of Rn, and I'm just going to write this down for now. I don't expect you to see exactly where this is coming from. The absolute value of Rn is equal to S minus Sn. That is less than or equal to the absolute value of Sn plus 1 minus Sn, and that is equal to An plus 1. All right, so I'm just going to write that down, and I'll try to explain it with a picture in a second. And the conclusion here is that the absolute value of the remainder is bounded by the first omitted term, and the term is An plus 1. Okay, so here's the takeaway. The error for an alternating series is bounded by the first term that you left off of that series. And this will become a lot clearer when I do the example in a second. But here's the formal theorem. Let me just read it along with you. We're going to let the sum from k equals 1 to infinity of negative 1 to the k plus 1, ak, be a convergent alternating series with terms that are non-increasing in magnitude. The remainder is defined to be S minus Sn. That's why we get this first equality up here. That is the remainder in approximating the value of the series by the sum of the first n terms. Then the remainder, the absolute value of the remainder, is less than or equal to An plus 1. So in other words, the magnitude of the remainder is less than or equal to the magnitude of the first neglected term. Okay. So everyone agrees that an infinite sum can be approximated by a partial sum, right? So if you want to estimate the true value of the alternating harmonic series, for example, you could estimate that by just taking the sum of the first 100 terms, right? But how close truly are you to the actual answer? In fact, you are no farther away from the actual answer than whatever the 101st term of that series is. So here's a picture to kind of help illustrate. The true value for the series is S. It is right there. Sn is some approximation for the series. It is up here. So it's kind of close, but there is some error associated with this partial sum. And that error is Rn. As we get more and more in, this Sn will actually get closer to the true value of the series. But the thing to note here is that Sn plus 1 minus Sn, since Sn was closer, we notice that the absolute value of Sn plus 1 minus Sn is actually equal to An plus 1. And the remainder is less than or equal to Sn plus 1 minus Sn, and that is An plus 1. I feel like I explained that terribly, but the takeaway here is just that the error is no larger than the first neglected term. Let's do an example. Consider the alternating series. We have negative 1 to the k over k squared. So if we write out the terms of this series, it's going to look like negative 1 over 1 squared plus 1 over 2 squared plus, or minus 1 over 3 squared plus 1 over 4 squared, etc. Find the third partial sum S3. So the third partial sum S3 is just going to be the sum of the first three terms. So negative 1 plus 1/4 minus 1/9. All right, if we throw that into a calculator, we are going to get that this is negative 31 over 36. All right, so here's our question. How close is this to the true answer of the sum? And I can tell you that using the theorem on the last slide, the remainder for our estimate here is no larger than An plus 1. So in this case, A3 plus 1. So that just means that R3 is less than or equal to A4. And so question for you guys, think about it for a second. What is A4? A4 is the fourth term of the series. So this was negative A1. This was positive A2. This was negative A3. And this was positive A4. If AK was equal to negative 1, AK is equal to 1 over k squared, then A4 is just 1 over 4 squared. Which in this case is just 16. So the remainder, R3, is less than or equal to 1/16. So here's the interpretation of what we have just said. S3 is equal to negative 31 over 36. And this estimate is no more than 1/16 off from the true value of the series. All right, so if we wrote down our series, looks like this. If we actually summed infinitely many terms here, our answer would be somewhere in the range of 1/16 or negative 1/16 minus 31 over 36 and negative 31 over 36 plus 1/16. So it is somewhere in that range. Okay, so that's a pretty easy test, in my opinion. All you have to do is check the first omitted term from your series. All right. Great, so let's continue on this line of thought. Let's now consider the alternating harmonic series how many terms of the series are required to ensure that the remainder is less than 10 to the negative sixth. So we did something very similar with the remainder test for the integral test. The idea here is that if we know that the remainder, Rn, is less than or equal to An plus 1, we are going to set An plus 1 less than or equal to 10 to the negative sixth and solve for n. Okay, and by doing this, we will be able to tell you how many terms are necessary to get the remainder to be less than 10 to the negative sixth. All right, so that's the basic idea. So, question, what is AK here? Well, AK is just 1 over k. Remember, it's everything except that negative 1 to the k plus 1 term. So, if AK is equal to 1 over k, then An plus 1 is equal to 1 over n plus 1. Right? We just replace that k with n plus 1. All right? And this is defined to be, once again, the first omitted term. Okay, so now let's set 1 over n plus 1 less than 10 to the negative sixth and solve for n. Okay, so once again, I use this arrow notation to go from one inequality to another inequality. So I can invert both sides. If I invert both sides, I have to flip the inequality. So 1 over 10 to the sixth is just, 1 over 10 to the negative sixth is equal to 10 to the sixth. And then if you subtract 1 from both sides, you get that n must be greater than 10 to the sixth minus 1. 10 to the sixth minus 1 is just 999,999. Okay. And so the statement that we write out is that, let me use a different color. So in order to ensure that the remainder is less than 10 to the negative sixth, we must add more than 999,999 terms of this series together. So if we want to get a really good estimate for what the true answer of this series is, we have to add a ton of terms together. In fact, more than 999,999 of them to get within an error that we can guarantee is less than 10 to the negative sixth. Okay? So now let's consider a very similar problem. We're going to consider the series sum from k equals 1 to infinity of negative 1 to the k over k factorial. We're now going to find an upper bound for Rn and approximating the value of the series with n equals 9 terms. Okay, so here's another way of thinking about this question, or another way to phrase it in your mind. Whoops. Let me erase that. All right, so here's another way to phrase the question, i.e., how big is the error if you only add the first 9 terms together? Wish I could write faster. This would be super nice. How big is the error if you only add the first 9 terms together? All right, so we're going to add negative 1 over 1 factorial plus 1 over 2 factorial minus 1 over 3 factorial all the way up to 9. All right? So the way to go about this is to once again use this theorem. We know that the absolute value of Rn is less than or equal to An plus 1. And Ak here is 1 over k factorial, which means that An plus 1 is going to be 1 over n plus 1 factorial. So this is 1 over n plus 1 factorial. So specifically, if we have n equals 9, R9 is less than or equal to A10, which is 1 over 10 factorial. And if we actually throw that into a calculator, this is approximately 2.8 times 10 to the negative 7. Which indicates that by adding only 9 terms of our series together, our error is really small. This is a really small error. And so we didn't need to add very many terms of this series together in order to get really close to the true answer of this sum. So here's a question for you to think about. Why did this sum require only 9 terms to get a really small error, whereas this sum required 999,999 terms to get a really small, to get really close to the true answer? Why is that the case? So I encourage you to think about that on your own time. If you have questions, you can always send me an email. All right, so now let's introduce another concept. We're going to talk about this idea called absolute convergence. And this will be super useful whenever we get to chapter 11. So the idea is pretty straightforward. The concept is that if the sum of AK converges, sum of the absolute value of AK, that's important, then the sum of AK converges absolutely. That's just a definition. That's what it means. If we take an absolute value around our AK, then it converges absolutely. And then the opposite direction, if the absolute value of AK diverges and the sum of AK converges, then the sum converges conditionally. All right, so I think that statement is somewhat confusing. So I encourage you to look at this chart to kind of think about what we're talking about here. There are 3 possibilities that we land in. Possibility 1, the series is divergent, right? So we start with the series, they ask us anything about this series, and it's just divergent, okay? That's the first category. The second category is if it is convergent, it can fall into 2 subcategories. It might be absolutely convergent, where if you took the absolute value, it would still converge. Or it might be conditionally convergent, where if you took the absolute value around AK, it is conditionally convergent. Okay? So Remember that conditional convergence happens when the absolute value diverges, but the regular series converges. Let's take a look at some examples. So we're going to determine if the following series converge absolutely, converge conditionally, or diverge. This first one is the alternating harmonic series. So we learned that this thing converged by the alternating series test. So that means that we are somewhere here, right? We are somewhere in this category. It is convergent, so it might be absolutely convergent, or it might be conditionally convergent. All right, so we know that it converges by AST, alternating series test. All right, so now we got to test if it's absolutely convergent or conditionally convergent. So we are going to test for absolute convergence. The way we do that is we are going to take the absolute value around our series. So I should be more careful. We're not taking the absolute value around the whole series, just around AK. So just like this, we're going to write -1 to the k all over k. And we're taking the absolute value there. We can simplify this. This can be written as just 1 over k, right? If you take the absolute value of -1 to the k over k, then it's just 1 over k. All right, question for you guys. Does this series converge or diverge? Think about it. This diverges. And it diverges because it is a p-series where p is equal to 1, which is less than or equal to 1. So let's write that down. All right, and so the conclusion is that since the original series converged and the absolute value diverged, that means that the sum from the beginning is conditionally convergent. Right, so let me go back here. We found that our first series was convergent, and then, whoops, not this one. We found that it was conditionally convergent because the absolute value of the sum diverged. Clean this up a little bit. All right, so let's write down our full statement. So, since the sum of -1 to the k over k converged, and the sum from k equals 1 to infinity of the absolute value of -1 to the k over k diverged, the original sum is conditionally convergent. All right, so the original sum converges, the absolute value diverges. Let's do another one. All right, so this time we have the sum from k equals 1 to infinity of -3/4 to the k. One thing we could do is we could rewrite this as the sum from k equals 1 to infinity of -1 times 3/4 to the k And one thing we know is that if we have ab raised to the k power, we can write that as a to the k times b to the k. So we could write this as negative 1 to the k times 3/4 to the k. So we can use the alternating series test to determine if this thing converges or diverges. So we can use the alternating series test. And the first thing we have to check, so we're going to define ak in this case to be 3/4 to the k. And the first thing we would have to check is if it is non-increasing. And in order to do that, I am going to recommend that we, actually, there's a pretty nice way to show that this thing is non-increasing. So remember I said that we can show that ak plus 1 is less than or equal to ak. So we have that 3/4 to the k plus 1. What's a way that we could rewrite that? Well, we could just rewrite that as 3/4 times 3/4 to the k. And that is certainly less than 3/4 to the k. And now, if I just give you a little bit of color, notice this was ak plus 1, and this is ak. So we have that ak plus 1 is less than or equal to ak. So it is indeed non-increasing. The second thing that we would have to check is whether its limit is equal to 0. So we have the limit as k approaches infinity of 3/4 to the k. And this is an exponential. We have a number raised to the k power. Since that number is less than 1, this thing indeed is equal to 0. So if you wanted any sort of explanation, you could write because 3/4 is less than 1. So this thing converges by the alternating series test. So some of you might be asking, why did we go through this trouble? There was an easier way to test whether this thing converged or diverged from the beginning, and in fact, you are absolutely correct. This original series, if you look closely, is a geometric series where r is equal to negative 3/4. And that the absolute value of r is equal to 3/4, which is less than 1. So that thing converged. And that was definitely an easier way to do it. So if you noticed that from the beginning, then props to you. You're absolutely keen on doing this stuff, and you should do that in the future. So yes, this thing converges both by the alternating series test and because it's a geometric series. Sometimes more than one test is applicable. All right, so that was the first part. We still have to check to see if this thing converges conditionally or absolutely. All right, so to test for absolute convergence, we have to examine the series sum from k equals 1 to infinity of the absolute value of negative 3/4 to the k. And if we simplify this, the absolute value of negative 3/4 raised to the k power is just 3/4 raised to the k. All right? And we use all of our tools in the toolbox to assess whether this thing converges or diverges. So this series will converge because it is a geometric series, once again, where r is equal to 3/4, which is less than 1. So this is a geometric series where r equals 3/4, which is less than 1, and so it converges. All right, and finally we write down the conclusion statement. So once again, we are now in this convergent case, but this time, when we took the absolute value, it converged also, so we are actually in the absolutely convergent case. So the series from k equals 1 to infinity of negative 3/4 to the k is absolutely convergent. All right, great. Next, let's consider this guy. Technically, we don't need to use the alternating series test as our first choice. We can use any test that is at our disposal. And in this case, what you might know is that this series will... let's actually check using the divergence test first. Okay, so let's use the divergence test and see if it works. See if it gives us any conclusion. So we're just going to take the limit as k goes to infinity of the whole thing, negative 1 to the k, over square root of k plus 2 over square root k. What is this thing equal to? I want you to take a second, actually try to figure out what this is equal to if you can. Pause the video if you need to. All right. The idea is, once again, just like we did earlier, we're going to consider even k and odd k. So if k is even, then we are going to get 1 because this thing, this negative 1 to the k, will just be 1. If k is odd, we would get negative 1. And what this indicates is that this limit doesn't exist. So the limit as k goes to infinity of negative 1 to the k, square root of k plus 2, all over the square root of k, does not exist because it oscillates between negative 1 and positive 1 as you get closer and closer to infinity. Therefore, by the divergence test, since the limit was not equal to 0, not equal 0, the series diverges. And we're done. There's nothing more to test. Remember, if we go back to our little chart here, if we land in the divergent case, then we're done. It's just divergent. There's no chance that it falls into any other category. And this fourth example is that we have the sum from k equals 1 to infinity of negative 1 to the k plus 1 times k squared divided by the square root of k to the 6th plus 1. All right, so this one is a little bit trickier. The thing that we would have to do for this guy is we need to check if the original series is convergent or divergent to start. So think about what test you would use to determine that. The one that I would use here is the alternating series test. So we're going to use the alternating series test. The first thing that we should do is we should identify what our AK is. We're going to call AK k squared divided by the square root of k to the 6th plus 1. All right. And so we have to check first, is it non-increasing? In order to do that, let's take a derivative. We have d by dx of x squared over square root of x to the 6th plus 1. All right, I'm going to skip a lot of steps here just for the sake of time. If you were to actually compute this derivative, you would end up getting 2x minus x to the 7th divided by x to the 6th plus 1 to the 3/2 power. And ask yourself, is this thing always less than or equal to 0? Well, the denominator certainly is. X to the 6th plus 1 is always greater than or equal to 0. Well, the denominator is always positive, but the numerator is negative whenever x is greater than 2. So if x was 1, for example, think about it, then we would have 2 minus 1, which is a positive number. But if x is equal to 2, we would have 4 minus 2 to the 7th. 2 to the 7th is 128. So yeah, that would be a negative number. So this is less than or equal to 0 for x greater than or equal to 2. Okay, and so that means that the original AK is not increasing after k equals 2, which is what we want. And the second thing that we have to check is whether the limit is equal to 0. And one thing that you might notice is that the numerator has a power of k squared. The denominator has a power essentially of k cubed, because the square root of k to the 6th is k cubed. So the power on top is smaller than the power on bottom. Therefore, this limit is 0, which is what we want. And so therefore, this thing converges by the alternating series test. So we are in the category where it converges. Now, is it absolutely convergent, or conditionally convergent? In order to check that, we need to take its absolute value. So now, is it absolutely convergent? Take the sum from k equals 1 to infinity of -1 to the k plus 1 times k squared over the square root of k to the 6th plus 1. And we are taking the absolute value of this thing. If we take its absolute value, we get k squared over the square root of k to the 6th plus 1. We basically just got rid of that -1 to the k plus 1 term. All right, now use any tool in your toolbox to determine whether this thing converges or diverges. Some things we've learned: divergence test. That will actually be inconclusive for this series because the limit is 0. We've also learned the integral test. This would be challenging to integrate, not impossible, but challenging. We also have the, let's see, what else do we have at our disposal? We know geometric series, but this isn't one of those. We have p-series. This isn't quite a p-series. What we learned last section, in 10.5, was comparison tests. So let's use one of those. So let's use, in this case, the limit comparison test. And we are going to compare it to basically the thing that this thing is approximately equal to. So k squared over square root of k to the 6th is approximately k squared over k cubed, which is just 1 over k. So let's take a limit. We're going to take the limit of, let me define AK to be this thing. So one thing you might notice is we use AK and BK a lot. They are just whatever we define them to be, right? So in this case, I'm defining AK to be k squared over the square root of k to the 6th plus 1. I guess switch back to green. All right, so this is going to be the limit as k goes to infinity of k squared over square root k to the 6th plus 1 times k over 1 this just gives me k cubed on top and square root of k 6th plus 1 on bottom, and this limit is equal to 1. Because the numerator power and the denominator power are essentially the same. You could further justify this by multiplying both the numerator and denominator by 1 over k cubed, and you would get that this answer is 1. All right, so if we remember the limit comparison test, basically, if we get any number between 0 and infinity, then both AK and BK have the same behavior. So we write out our conclusion statement. Since the sum from k equals 1 to infinity of 1 over, let's see, how did we write it last time? I think we want to say something slightly different. Okay, since L is equal to 1 and the sum of 1 over k diverges, we explain why that diverges. It is a p-series with p equals 1, which is less than or equal to 1. since L is equal to 1 and the BK diverges, then our original series sum of AK diverges also. Okay, that was a lot to go through. And so now, finally, we get to the point where we can make our conclusion about the original question. The original question was, does the series converge absolutely, converge conditionally, or diverge? And in this case, it converged originally, and then when we took the absolute value, it diverged. So this this converges conditionally. So the sum from k equals 1 to infinity of negative 1 to the k plus 1 times k squared over the square root of k to the 6th plus 1 converges conditionally. All right, great. And last theorem for this section, theorem 10.9. Absolute convergence implies convergence. So basically, the theorem name tells you everything you need to know. If the absolute value of the series converges, then the original series converges also. So absolute convergence implies regular convergence. Equivalently, if the original series diverges, then the series of the absolute value diverges also. So here's a quick example. We're going to consider the series from k equals 1 to infinity of negative 1 to the k plus 1 times k plus 1 over k cubed. That is just equal to k plus 1 over k cubed. And think to yourself, does that converge or diverge? That converges. We can justify this by doing a comparison test. I won't write out the details, but that indeed does converge. It's also, if you split up the numerator, you could write it as two different p-series. So either way, it converges. So that means that our original series has to converge also. So the absolute value converges, so the original series converges. That's basically what we're saying. Now we're going to come up with our own example for the divergent part. And basically just come up with your favorite divergent series that you can think of. So for example, sum from k equals 1 to infinity, negative 1 to the k times k, all over k plus 1. This thing diverges, so our original sum diverges also. All right, and that's all I've got for this section. Yeah, if you have any questions, feel free to let me know. I'm always happy to answer them. Talk to you guys later.